Okay, let's talk a little bit about derived dimensions that may get you into some trouble if you're not careful. So density. If you think about the equation for density, the variable used for density is frequently the Greek letter rho, and it's defined as the mass of a substance divided by the volume of the same substance. So we have fundamental dimensions for mass, that's a capital M. By now, hopefully you reflexively know the fundamental dimensions for volume as a length cubed. So we can write the dimensionality of density as a mass per length cubed. So why you have to be careful with these kinds of derived dimensions is other derived dimensions might have the exact same dimensions even though they mean something different. For example, concentration. One of the ways we measure concentration is to take the mass of a solute over the volume of a solution. Well, there's fundamental dimensions for mass in the numerator. You end up with fundamental dimensions of, derived dimensions of volume in the denominator, and you end up with the exact same dimensions, mass per volume. So this is just an indication that you can't look at the dimensions alone and know exactly what it means. The context matters. Mass of what? Volume of what? So the dimensionality is an abstract concept. It helps you think about how to map numbers to reality, but you need to understand the context of the fundamental dimensions before you're going to have that full understanding. So just the M's and L's don't tell you everything. You've got to know a little bit more. Also, there can be the same variable or the same property that is characterized with several different dimensions. For example, sometimes concentrations are represented by a mass ratio, a mass of the solute to the mass of the solution. Well, those both have fundamental dimensions of m, and if you let those m's divide out, you're going to have a dimensionless number for concentration. It's still a concentration, but the number means something very different. Concentrations are also sometimes represented by a volumetric ratio. If you look at your can of beer, you're going to see that the alcohol content is probably represented as a volumetric ratio or a volumetric percent. Both of those volumes are length cubed. If you let those length cubes divide out, you end up with a dimensionless number, which is a different dimensionless number than the mass ratio. You could also have molarity, which is the number or the count of molecules of the solute divided by the volume of the solution. Again, that n is a count. It has units of moles, but it's just a unitless number because it's just a count. The concentration in the denominator is length cubed, so, the volume in the denominator is length cubed, so a concentration in molarity just has the dimensionality of per volume. There's nothing in the numerator, just a per volume. You might have a mole ratio, which is the number of moles of the solute over the number of moles of the solution. Again, those are both counts. They'll divide, they don't even need to divide out because they're both counts, and you end up with a dimensionless number. Another way of using a dimensionless number to characterize concentration. So you have three different dimensionless approaches to characterizing concentration here. Sometimes we don't let dimensions divide out. Because that context matters, mass of what, volume of what, sometimes you want to let them go. You want to leave those dimensions in there. For example, if you want to be super clear that your variable is a mass ratio, or your concentration is a mass ratio, you can perfectly validly show its dimensionality as a mass per mass. And that way you're being abundantly clear that your particular dimensionless ratio that you're using is based on mass, and you can make it clear to somebody reading your work that is a mass ratio and not a volume ratio or a mole ratio. Same thing can be done with volume, where you can specify it's a length cube per length cube. So sometimes for the sake of clarity, you don't necessarily want to simplify your dimensions all the way because you can distinguish dimensionless numbers from each other by showing which dimensions actually divide it out. That's actually a pretty common thing to do. It's also pretty common to do with units. If you're showing a mass ratio, you can show like gram per gram as opposed to just showing it as unitless. And it's valid and unambiguous to do that.